In this video, we'll talk about the Poisson limit theorem and introduce a useful discrete distribution called the Poisson distribution. Before introducing the Poisson distribution, let's start with the familiar binomial distribution. Let X be a binomial NP random variable. Then in previous videos, we have calculated that the distribution of the binomial NP random variable can be described by this formula. This formula has a component that's n choose x, and also a component that's p to the power x times 1 minus p to the power n minus x. Here p is the probability for the event to happen in one trial, and n is the number of trials, and x is the number of successes in the n trials, or number of occurrence in the n trials. This formula is not hard to write down. It's not very complicated. However, it can be really difficult to compute when n is very large. And in some situations, we encounter very large n's. The following is an example where we encounter a very large n. In this example, suppose that you are appointed the director of a hospital, and you want to know how many ventilators to buy. So what's relevant for your decision is the number of patients arriving at your emergency room in need of a ventilator. So let X denote that random variable. You do not know how many people will arrive at your emergency room needing a ventilator on any given day. And that is the random variable that you are interested in. Well, it's very reasonable to model this random variable as a binomial random variable. You can think about it in the following way. Suppose that your hospital serves a population of 10,000 people. Suppose that is the number of people living in the surrounding area of your hospital who could reasonably come to your hospital when they need medical help. And each of these 10,000 people has a chance, maybe a very small chance, but each of them has a chance to need to go to your emergency room in need of a ventilator. Each of these people may need a ventilator with a probability. Granted, this probability is typically very small, but because you got 10,000 people that your hospital is serving, so on any given day, there is a good probability that some of them will be there and need ventilator, and you want to have some idea of how many. And if you think about X this way, then it's logical to say that X is a binomial random variable with parameter n and p. But you know it is a binomial, but for this binomial distribution, the n is huge. Suppose you want to calculate the probability that X is greater than 3. What's the probability that you need more than 3 ventilators? Then you're gonna have to sum up all the X sum up the probability that x equals little x for x from 3 to n, which is 10,000. 10,000 choose x times p to the power x, 1 minus p to the power n minus x, where n is 10,000. This is quite difficult to compute just because 10,000 is a huge number. If you have 10,000 factorial, 10,000 factorial is a number that most computers cannot even handle. And not only that, but also you have a probability to the power 10,000 minus x. And that's a huge number to take to calculate this power for. So this is hard to compute. And if you try to compute this for a reasonable x value on your computer, your computer will tell you that your result may not be accurate. The reason is you are multiplying a huge, huge number to perhaps a very small number. And in this situation, computers don't give you very accurate results. So binomial distribution is hard to compute when n is very large. Fortunately, when n is very large and p is very small, we can approximate the binomial distribution with a much simpler distribution. And that is what the Poisson limit theorem is about. How do we think about this approximation? This approximation applies when n is large and p is small. How do we mathematically represent the situation where n is large and p is small? Well, we can use the calculus concept of limit. So we want to consider the limit of the probability that x equals little x when n approaches infinity, when n grows to infinity, and p accordingly gets smaller as n grows to infinity. So we consider the limit of this probability as n goes to infinity and p also changes with n, but proportionally to the inverse of n. So p equals lambda divided by n for a positive number lambda. So as you can see, when you take this limit, n is growing very large and p is growing, converging to 0. P is diminishing to 0, but at a rate that is controlled. So we take this limit and see what we find. We do this on this next page. So we consider the limit of this probability as n approaches infinity and p equals lambda over n. So that is the limit of n choose x. Actually, I want to write n choose x out using the formula for this combinatorial quantity. Remember that is n times n minus 1 times n minus 2 until you are at n minus x plus 1 divided by x factorial. So that is n choose x times p to the power x, where p is lambda over n to the power x, and 1 minus lambda over n to the power n minus x. So we do this. Now, notice that this x factorial part doesn't depend on n, and lambda to the power x also doesn't depend on n. So these are constant. We can pull out of the limit. So we have lambda to the power x divided by x factorial limit n minus 1 to n minus x plus 1 divided by n to the power x, which is n times n times n. And there are x number of n's on the bottom, and there are also x number of terms on the top. And also that times 1 minus lambda over n to the power n times 1 minus lambda over n to the power minus x. Now we copy lambda to the power x and x factorial right here, and look at each term after the limit. For the first term, as you can see, it's n divided by n, which is 1. N divided by n times n minus 1 divided by n, which also has limit 1, to n minus x plus 1 divided by n. All these x terms, each of these x terms have the limit 1, because when n is approaching infinity, x is fixed. So the limit of this ratio approaches 1. So all of these approach 1, their product also approach 1. And for this third term, we are taking n to infinity. The power doesn't depend on n, so the limit can be taken inside the parentheses. When n approaches infinity, lambda over n approaches 0, and 1 minus lambda over n approaches 1. So this part approaches 1 to the power minus x. So that's also, so that should be 1 to the power minus x. And for this part, the second part, I'm gonna claim that it equals a number, and I will explain that number right away. So the limit of all of these terms is 1, limit of this term is 1. So the limit of this term, I will claim that it is a mathematical constant e to the power minus lambda. And this formula is exactly the distribution function of the Poisson random variable. So the Poisson random variable which has a parameter lambda is exactly this. Lambda to the power x divided by x factorial times e to the power minus lambda. And realizations of the Poisson random variable can be 0, 1, 2, to infinity. So all the positive integers and 0. So that is the Poisson distribution. the Poisson lambda distribution. And I will explain this E number later. Just look at the Poisson distribution formula. It no longer involves the huge number n. And it does not involve p to the power n minus x. So all the quantities involved here are of manageable scale, and it's easy to compute this number accurately. So that's why using the Poisson distribution to approximate binomial can give you more accurate answer to probabilities of certain events. That's when n approaches infinity and p approaches 0 proportionally with 1 over n. Now let me explain the number e. Remember, this e to the power minus lambda is obtained from the limit of this. And that's actually one definition of the constant e. The constant e is a mathematical constant, like pi is a mathematical constant. It is an irrational number. The value of it is approximately 2.718, but it's got infinite number of digits. What's the definition of E? One definition of E is through this formula right here. E is defined to be the limit of this quantity, limit of 1 plus 1 over n to the power n. And this is the definition of E. And this definition is called the continuous compound formula. Continuous compound formula. Compound comes from compound interest. So it has a basis in computing the compound interest. So consider that you are opening a bank account that pays you an interest. Suppose that the bank pays an annual interest rate of 100%. Okay, the bank pays an annual interest rate of 100%. You put in $100 to the account, and you want to know how much money you get at the end of the year, after 1 year. Well, that depends on how the bank pays the interest. If the bank pays the interest once a year, then what you get is 100 times 1 plus 100%. So you get $200. So that's 100 times 1 plus 100%. If the bank pays the interest only once a year, so there is no compounding. It just pays you a 100% interest rate at the end of the year. But if the bank pays the interest twice a year, so the bank pays you an interest at 6 months, and then the 6 months you don't take out the interest, you keep the interest that the bank pays you in your account, and that interest again becomes your principal, and that also earned an interest for the next 6 months. So that's called compounding, right? So if the bank does that and you keep that, if the bank pays you an interest twice a year and you do not take out the interest when the bank pays, then what you will have at the end of the year is 100 times 1 plus 100 divided by 2 squared. So why do you get that? The reason is at the 6-month mark, you get 100 times 1 plus 100% divided by 2. That's what you get at the 6-month mark. But you're keeping this much money for another 6 months, for another half year. So that's gonna earn you an interest and also the principal will be back to you as well. So that's going to be your principal. And after 6 months, the principal and the interest becomes that times 1 plus 100% divided by 2. So that's how much money you will have when the bank pays the interest twice a year and let you compound the interest. If the bank pays you an interest rate at 12 times a year, that's quite common, like monthly. If the bank pays you monthly interest, then what you're gonna get is 100 times 1 plus 100% divided by 12 to the power 12. 100% divided by 12 is the monthly interest rate, and raised to the power 12 is because you're keeping the money in the bank for 12 months. And similarly, if you keep the money in the bank for a year and the bank pays daily interest, then what you get in the end is 100 times 1 plus 100% divided by 365 to the power 365. You can continue this process. You will see that this number, the final amount of money that you have, is bigger and bigger as the bank pays the interest more and more frequently. And you continue this process and ask the bank to pay you even more frequently, like every hour or every second or every millisecond. Continue the process, and this sequence of the money that you get at the end of the period will turn out to be E. So, and that number is the continuous compound multiplier. Okay? If the bank continuously compound your interest, then what you get is 100 times this limit, which is 100 times E. So E is the multiplier you get when you save money in an account that pays an annual interest rate that's 100%, and when the bank pays you interest continuously. So that is what E means. So by definition, E is the limit of 1 plus 1 over n to the power n. And what we have in the Poisson limit theorem calculation is not 1 over n, but 1 plus minus lambda over n. What you have is 1 plus minus lambda over n. How do you get that? Well, we can first get, let me actually try to do this from scratch because that might be more clear. So what you want to get this, what you have is this. How do you go from there to here? First, let's consider limit of 1 minus lambda over n to the power n. And you can write that as limit n minus lambda divided by n to the power n. And you can write that as n divided by n minus lambda to the power n, but then to the power minus 1, because you flipped the numerator and the denominator. The purpose of doing that is to create something that looks like the definition, look like the formula in the definition of E. So once you do that, inside we find that equals 1 plus lambda divided by n minus lambda to the power n and then to the power minus 1. Now I can continue this and write what's inside as 1 plus 1 over n minus lambda divided by lambda, which didn't change anything. I simply moved the lambda to the denominator. And the power n, I will write that as n minus lambda divided by lambda, but also to the power lambda. So this lambda and that lambda cancels out, so this is this quantity to the power n minus lambda. We are still short of something, right? So we're still short of this quantity to the power lambda. So we make it up by multiplying that quantity by 1 plus lambda over n minus lambda to the power lambda. And outside, we still have this power minus 1. So what did we do? We obtained a form of this that looks exactly like what's here. So what we do next is to move this limit into these functions. Here the minus 1 doesn't depend on n, so we can move the limit into this inverse function. So that equals the limit n to the power n approaches infinity. I will take the limit all the way into the power lambda function. And also times the limit of 1 plus lambda over n minus lambda to the power lambda. And then outside you still have the inverse function. Now look at this limit. I'm going to do a change of variable and define n minus lambda divided by lambda as m. So I will define this as m. So inside we have limit n goes to infinity, implies that m also goes to infinity because m equals n minus lambda divided by lambda, where lambda is a positive number, fixed positive number. So when n approaches infinity, m also approaches infinity. So that limit can be written as limit of m, limit as m goes to infinity, 1 plus 1 over m to the power m, and outside to the power lambda. Now, if you look at this term, this lambda is fixed, the power is fixed, so the limit can be taken inside this power function. So this limit equals the limit of 1 plus lambda over n minus lambda to the power lambda. Well, the limit of lambda over n minus lambda is 0. So the lambda of 1 plus lambda over n minus lambda is 1. So the limit, this limit equals 1 to the power lambda, which is 1. Therefore, we obtained this formula. Now in this formula, observe that this limit inside this lambda power function, this limit is exactly the same as this limit on the right-hand side of the definition of E, except we have n here but m here. But that doesn't matter because that's just a notation. So you can, so we see now this limit equals E. So that limit equals E. In the end, we have E to the power lambda and then to the power minus 1. So we have E to the power minus lambda. And this is how you got this result. So that's how you get this result. So, and when we come back here, you see that we just proved the limit of this term is e to the power minus lambda. So that shows that the limit of the binomial distribution is the Poisson distribution as n goes to infinity and p equals lambda over n. And this lambda here is called the Poisson arrival rate. The Poisson distribution is often used to model a situation just like the emergency room arrival that we talked about. And it's used to model the number of occurrences of events, of rare events usually, because if it's not rare events, then the p is not approaching 0 with n. And when p is approaching 0 at the rate 1 over n, the events, the probability that the event happens is small when n is big. So therefore, the event is a rare event. So Poisson distribution is often used to model the number of occurrences of rare events. Some examples include the number of V2 bombs V2 bomb strikes in each small square in London during the World War II. And this example is described in more detail in the book as well. Or maybe Poisson distribution can also be used to model the number of visits to a not very popular web page each day. For the Poisson distribution, you can calculate its traits. We're not going to go through the mathematics in the book. There is the mathematics, there is details for deriving the traits of the Poisson random variable, but we'll not go through that. But I will just mention that a Poisson lambda distribution has expectation that equals lambda. And coincidentally, Lambda is also the variance of the Poisson distribution. So for Poisson lambda distribution, both the expectation and the variance are the same and they are equal to lambda. Another special feature of the Poisson distribution is that when you have two independent, which is important, two independent Poisson distributions, one is Poisson lambda 1, the other is Poisson lambda 2, then the sum of the two is also Poisson with parameter lambda 1 plus lambda 2. So this is not surprising, and it's quite intuitive when you think about this emergency room arrival example. So suppose that x1 is the number of arrivals from the west part of the city, x2 is the arrival from the east part of the city, and x1 plus x2 is the number of arrivals from both parts of the city. Then it seems intuitive that these two should be, the distribution of the two should be additive in this way. So when you add up two independent Poisson distributions, you get another Poisson distribution. And that's all.